Welcome to the second part of Building Robots, System Integration. My name is Gaspar Škulj from University of Ljubljana, and today we'll learn about 3D printing as an enabling manufacturing technology for building robots. We will start with the process of 3D printing, focusing on commonly accessible FDM technology printers. Next, we will list common problems and possible solutions. At the end, we will look at this week's project assignment. The idea of 3D printing is to create a part using an automated machine that is adding a lot of small pieces together based on a predefined program. If we only focus on easily accessible FDM 3D printers, where FDM stands for Fused Deposition Modeling, the process is quite simple. The raw material is in a form of thermoplastic filament with a constant diameter wound on a spool. The filament is pushed through a heated nozzle where it melts and exits out of a hole with a known diameter on a surface where it cools and hardens. The nozzle is moved and extrudes plastic where material should be deposited and skips parts where material is not needed. To create a part, a systematic approach to moving of the nozzle is needed. The path of the nozzle and where to extrude the material is obtained by slicing the 3D model of the part into thin layers. Path for each layer is then determined to create a nice outer surface and only partially filled part. First, the bottom layer is extruded on the printer's bed. After the first layer is complete, second layer is added on top of the first layer. After that, the third layer on top of the second, and so on until all layers are extruded and whole part is created. This simple idea allows us to easily design any part in 3D modeling software and have it automatically created by a machine on our desktop. The machine and the raw material are relatively affordable, especially for the case of prototyping, allowing for fast iteration of our design. The workflow of manufacturing with 3D printing is as follows. First, it is good if we know the capabilities of the 3D printer we will use. Common information are nozzle output diameter, supported materials, build plate size, and maximum build height. Based on this limitation, we can design a part and export it in a format supported by a slicer program for the 3D printer. In the slicer, we position the part on the build plate, select the printer and the material we want to use. While it is possible to use custom configurations for the printers and materials, it is recommended that the default manufacturer's configurations are used with small changes if needed. For example, if we use Prusa printer, we should also use the Prusa Slicer program where the specific configuration for our printer is added. For the filament material, we can select vendor-specific configuration or a generic one. Different materials have different melting temperatures, however there is a relatively wide range of acceptable temperatures usually specified on the filament spool. For the slicing process, there are some parameters that we need to specify or at least check. First is filament diameter that needs to match with the filament we will use. Next is the nozzle diameter and layer height. Smaller diameter and layer height allow us to print finer details. Then we can specify infill percentage and pattern so that the part will be partially hollow. We can do that because the part strength is mostly determined by the outer walls. We can also enable support structures if our part will be printed with overhangs, but that is something we want to avoid. Finally, we run the slicing procedure that generates the nozzle path program. We then save and transfer to the 3D printer. Before running the 3D printer, we check that the correct material and nozzle will be used. After that, we can initiate the printing process. the printer loads the filament, heats up the nozzle and the build plate. Then it follows the print program until all layers are extruded. The printing time depends on the size of the part and is most significantly influenced by the number of layers. At the end, nozzle is moved to the side, everything cools down, and we can move the part from the build plate. Ideally, the described 3D printing workflow will allow us to create a part of any shape we want. Unfortunately, there are limitations. First, 3D printing process is limited by the fact layers are being stacked on top of one another. The layers, even if they are very thin, will show on the side surface of the part. Strength of the part is also dependent on layer orientation. The part has least tensile strength in the direction of layer stacking and will most readily fail where two layers are bonded, causing delamination. We also can't extrude plastic without support underneath. Extruded material will sag relative to the unsupported length. So short segments without supports are possible, otherwise dedicated support structure is needed. Support structure is later removed, but the supported part surface will have significantly worse finish. Second problem is related to the width of extrusion that is directly related to the material flow rate and rely on constant filament diameter. If the flow rate is not the same as assumed by the slicer, the part dimensions will be different from the dimensions of the model. Usually, the printer extrudes a bit more than assumed, making parts wider and holes narrower. Extrusion start and stop point also produce surface artifacts that, if stacked, create a noticeable seam. If the printing filament contains moisture, it will vaporize during melting of the filament and cause uneven material flow that results in poor part tolerances and surface finish. Final important problem that we'll mention is first layer adhesion to the build plate. This is a crucial part of the printing process that determines stability of all other layers and part as a whole during printing. If the material that is being extruded doesn't adhere well to the build plate material, some parts of the bottom layer could be missing when starting the second layer. That will, in some cases, totally prevent further layer stacking and extruded material will build up on the nozzle. First layer can also lose its adhesion with the build plate because of thermal stress after layers on top are added and cool down. This will cause warping or even detach the part from the build plate, ruining the possibility for successful continuation of the process. The best way to address the fact that 3D printing is using layer stacking to build a part is to design a part for this particular manufacturing technology and its limitations. This general solution applies for any manufacturing technology, so a more concrete design advice for 3D printing is to start the design with features of the first layer that should ideally be the widest and flattest segment of the part, providing a good build plate adhesion and stability. Features should then be extruded in the direction of layer stacking so that side surfaces don't form overhangs with angle greater than 45 degrees. When deciding on part shape and surface of the first layer, load that will be exerted on the part is a major factor. Tensile load in the direction of layer stacking should be avoided. Otherwise, part cross-section should be made larger to prevent delamination. Important geometric features should be positioned on planes parallel with printing layers because resolution on the printing layer is much higher than in the direction of layer stacking. Holes or gear teeth are nice examples of such features. If features are small, their dimensions should reflect nozzle extrusion diameter. For example, thin wall should ideally have the width that is a multiple of nozzle extrusion diameter. Feature with small dimensions in the layer stacking direction should also be a multiple of layer height. For relatively larger dimensions, that is less important. Additionally, where there is a fit with another object, more space should be designed between them to account for over-extrusion and surface artifacts. Alternatively, post-processing by removing excess material is possible, but not desired, as it requires additional time and manual labor. One common example is widening of the holes with a drill or sanding of the small surface artifacts. If large part modifications are needed, it is better to correct the part model and make a new print. To avoid problems during the printing process, quality filament with constant diameter should be used and also dried before printing. To assure good first layer adhesion, heated build plate with correct material and texture should be used and cleaned before printing. Dust or fingerprints could prevent good adhesion. It is also recommended to supervise the printing of the first layer to spot early signs of print failure, like poor adhesion, slight popping sound if the filament has excessive moisture, or under extrusion because of problems with filament feeding or incorrect temperature. Importance of understanding the selected manufacturing process when designing a part is in the possibility to lean into its strengths and avoid its limitations. For 3D printing, its major strength is the possibility for fast and inexpensive iteration of designs that can be hard to produce otherwise. 3D printing is also almost entirely automatized and allows the user to work on something else while the part is being produced. 3D printers are now, because of that, also very accessible and a common tool in the prototyping workshops. Possibility of making changes to the 3D printed part locally and fast makes the system you're designing more flexible because those parts can be adapted to parts you can't easily change. The concept designed for manufacturing and assembly can and should be applied to any manufacturing process, not just 3D printing. The robot we're trying to build has many 3D printed parts. Because we are using a small DC motor in our drivetrain, we need to use a gearbox to get appropriate torque and rotation speed for the wheels. One possible solution would be to buy a suitable geared motor. However, we want to create an educational robot, and by making custom gears, we can learn a lot about 3D printing. The gearbox for the servo motor of the robot has to have a high reduction ratio so that we will use the DC motor efficiently. We also want for the robot to move relatively slowly and with precision. Gearbox ratio can be determined based on the desired maximal rotational speed of the output shaft and rotational speed of the DC motor at maximal applied voltage. This speed is reached if there is no load. Because there will be losses in the gearbox, real speed will be lower. For our case, we estimated that we need a gear ratio of 243 to 1. That means the motor rotates 243 times for one rotation of the output shaft. To get such reduction with a single stage using motor gear with 12 teeth, the output gear would be required 2,916 teeth and would be enormous. If we create the gearbox with 5 reduction stages, things become more manageable. Now each stage has smaller gear with 12 teeth and larger gear with 26 teeth, creating 3:1 reduction ratio. Size of the gear depends on the number of teeth and size of single tooth or module. Because we want To print the gear, there is a limit to how small the tooth can be, and it depends on the nozzle extrusion hole diameter. For the servo motor, module 1.5 mm is used. Shape of the tooth also depends on pressure angle and clearances. Center distance for meshing gears depends on pitch diameter and is determined by the number of teeth for both gears multiplied by the module divided by 2. Your task is to create a Hello World example for a single gear pair that can be 3D printed. In CAD, create one small gear with 20 teeth and one large gear with 60 teeth and simple connecting structure with 2 axles that can be 3D printed. Gear height can be approximately 3 mm. Use tutorial for FreeCAD and Prusa Slicer to prepare the necessary files for a 3D printer. In CAD files for the GEMS servo motor, you can also find examples of gear designs that can help you. Because mechatronic system design is an iterative process, it is beneficial to use manufacturing technologies that support fast development pace, such as FDM 3D printing. 3D printing has its limitations that should be considered during design process to avoid problems during implementation and integration. However, it is easily the most useful and versatile manufacturing technology to use when creating a robot. Thank you for watching.